All right, everyone, welcome. So today we're going to roll up our sleeves and tackle a really classic problem. Think like engineers. How do we build a network for the absolute cheapest price possible? And along the way, we're going to get to know a really beautiful and elegant algorithm called Kruskals. Okay, so let's set the scene. Imagine you're in charge of wiring up our entire campus. You've got the main building over here, the library way over there, the dorms, the labs, they're all spread out. And your job? Connect every single one of them with high-speed fiber optic cable. Now, as you can imagine, that stuff is not cheap, and the cost to run a cable between any two buildings is totally different. So that leads us to the big question, right? You've got this map, and it shows you exactly how much it costs to lay cable between any two buildings. How in the world do you pick which cables to lay so that every building is connected, but you spend the absolute least amount of money? This thing we're trying to build, it actually has a name. It's called a minimum spanning tree. That's just a fancy term for the cheapest network that connects every single point.
All right, so when you're staring at a problem like this, what's your first instinct? The most, human way to start. You'd probably go for what we call a greedy approach. And yeah, it's pretty much exactly what it sounds like.
So what's a greedy method? It's super simple. It just means that every single step, you make the choice that looks best right now. You don't think about the future, you don't worry about the consequences down the line, you just look at your immediate options and pick the best one. In our case, the cheapest one.
Okay, so let's apply this greedy strategy to our campus network. It would go something like this. First, you list out every single possible connection and how much each one costs. Step 2, you just find the absolute cheapest, shortest connection on that entire list and say, yep, let's build that one. Then you find the next cheapest one and build that. You just keep going, picking the cheapest available connection one after another. Sounds pretty easy, right?
Yeah, it sounds simple, maybe a little too simple. Because, if we just follow this strategy blindly, we are going to run into a huge problem, a really expensive catch that could totally wreck our plan to save money. And that catch, well, it brings us to the single most important rule in this whole problem. I like to call it the no loops rule. This right here is the secret sauce. It's what turns our simple greedy idea into a really powerful and, more importantly, a correct algorithm. So what's a loop? You might also hear it called a cycle. Basically, it's a path that lets you start at one building, visit a few others, and end up right back where you started without ever having to backtrack. Now, in our campus problem, a loop is just pure waste. It means you spent a ton of money on a cable connection that is completely redundant. You just don't need it.
Okay, so this is the key difference you've got to understand. A good connection, that's one that connects a brand new isolated building to our network, or it merges two totally separate groups of buildings together. But a bad connection, one that creates a cycle, is one that connects two buildings that are, surprise, already connected through some other path. They're already in the same group. That's the huge difference between actually growing your network and just wasting money on extra wire.
So this really brings our problem into focus. The real challenge isn't just grabbing the cheapest connections. It's about grabbing the cheapest connections, but having a smart rule in place that can tell us, whoa, hold on, don't add that one. It's going to create one of those wasteful loops. And the algorithm that pulls this off perfectly? You guessed it, it's Kruskals.
All right, time to see this thing in action. Kruskal's algorithm is it's so elegant. It takes that simple greedy idea we talked about and combines it with that super powerful no loops rule. It's all about making the cheap choice, but with one absolutely critical check every single time.
Step 1 is always the same. It's non-negotiable. Before we even think about anything else, we take all the possible connections, we call these edges in graph theory, and we sort them, from the cheapest one all the way to the most expensive one. So looking at our example here, you can see that connecting Building 2 and Building 6 is our cheapest option, with a cost of just 10.
Okay, now for the fun part. We're literally just going to walk down this sorted list, one connection at a time. And for each one, we're going to ask a very simple question. The answer to that question tells us everything. Do we build this connection, or do we throw it in the trash?
First up on our list, the cheapest of the cheap, connecting 2 and 6 for a cost of 10. So we ask the question, are buildings 2 and 6 already part of the same connected group? Well, since we're just starting, nothing is connected to anything, so the answer is a big no. Our action? We accept it. We lay that cable, and now we have our very first connected group, the set containing 2 and 6. Okay, next on the list is connecting 3 and 4, with the cost of 12. Same question. Are 3 and 4 already in the same group? Nope. They're totally separate from our first group, the 2-6 one, so we accept this one too. Now our network kind of has two little separate islands of connection. We've got the 2-6 group, and now we have this new 3-4 group. All right, let's keep it moving. The next edge is between 1 and 2, and it costs 25. So, is building 1 already connected to building 2? Well, let's see. We know 2 is in that 2-6 group, but building 1 is just out there on its own. So, no, they're not in the same group. We accept this edge. And what this does is it merges building 1 into that first group. So now we've got one big group, 1, 2, 6, and our other group, 3, 4, is still just hanging out by itself. Okay, let's take a quick pause here. This next step is where the algorithm really starts to get smart. The edge we're considering now is 2, 3, and it has a cost of 28. So is building 2 in the same group as building 3? Let's check. Building 2 is in our big 1, 2, 6 group, and building 3 is in that 3, 4 group. They're in different groups, so we accept it. And watch what happens now. This connection merges our two separate islands into one. Our one big connected group is now 1, 2, 3, 4, 6.
And now, the moment of truth. This is the big one. The next cheapest connection is between 1 and 4, with a cost of 30. So we ask our all-important question. Are buildings 1 and 4 already in the same connected group? Let's have a look. And yes, they are. They both belong to that massive group we just formed. So if we were to add this connection, we create that wasteful loop. So for the very first time, our action is to reject. We throw this edge out and move on. And just like that, we saved ourselves 30 bucks, or whatever our cost unit is.
And that right there, that is the heart of Kruskal's algorithm. That one simple question, are these two things already in the same group, is how we enforce our no loops rule. Now, in computer science, there's actually a perfect tool for this job. It's a data structure called a disjoint set, and it's designed to do two things super fast. Check if two items are in the same set, and merge two different sets into one. It's this powerful tool that makes Kruskal so fast and efficient. Okay, let's wrap this up. Now, if you're studying for an exam, you're going to want to pay very close attention to this next slide. Think of this as your cheat sheet. It's everything you need to know about Kruskals, all boiled down.
So, here's what you absolutely need to know. First, what's the goal? We're building a minimum cost spanning tree, a network that connects everything for the lowest possible price. Second, what's the method? It's greedy. That means we always sort the edges and check the cheapest one next. Third, and this is the most important part, the rule. You have to check if an edge's two buildings are already connected. If they're in the same set already, you reject it. No loops. If they're in different sets, you accept it, and you merge those sets together. That's it. That's the whole thing. And there you have it. It's a really simple idea, but it's so incredibly powerful. You just sort everything first, and then you go down the list, intelligently checking for loops. And by doing that, Kruskal's algorithm guarantees you'll find the absolute cheapest way to connect everything. And this logic, it's not just for laying cables on a campus. It's used in computer networks, designing circuits, planning logistics, you name it.
So, I'll leave you with a little something to chew on. What if our problem was just a little bit different? Imagine we weren't laying cable, but we were building roads. And what if the cost to drive from building A to building B was different from the cost to go from B back to A? Maybe because there's a big hill in one direction. How would something like a one-way street change our whole greedy approach? Give that some thought. We'll catch you in the next one.